Hello, we're really getting into the nitty-gritty of it now. Today we're going to be using some proper statistical tests which you'll be using in the future. It's been a bit dry in the last two videos, but if you've watched them and understood them, then you're really going to get the value of it now, because we're going to show you how confidence intervals and standard error of the mean link to the results of all the statistical tests which we look at. So for this we're going to go back to the lap hernia dataset, laphernia.sav, so you should have that in on your home drive. The core reading for this is the Chapter 6 p-values and Chapter 7 the t-test values. You don't really need to read them cover to cover, but they're useful to refer to. In this video I hope we will cover what we mean by a p-value, what a t-test is. We will link confidence intervals and standard error of the means to what we're doing, and we will be answering the question, how do I compare the means of two groups? So for instance, the pain score of someone who's had an open hernia repair versus the pain score of a group of patients who have had a laparoscopic hernia repair, the mean of those two groups of pain scores, how do we determine whether the means are different or not? We'll be back to using frequencies, but we'll be introducing the t-tests in SPSS, and we're also going to try and explain this with histograms. So open lap_hernia.sav, and this is what you should see. First of all, we'll get our descriptive data back up using the frequencies function. So scoot across pain score, and for this we're just going to look at pain score for all the patients. We're not going to look at any subgroups at the moment, so just pain score. Statistics, let's look at the quartiles, add in the mean, the minimum, the maximum, and the standard error of the mean as we did before. Unclick display frequency tables and click OK. So this is what we have, 50 valid measurements with a mean of 4.4, a median, which is the 50th percentile, of 4.6, and a standard error of the mean of 0.24. Next, we want to bring up a histogram of pain score. So go to Graphs, Chart Builder. On the list on the left hand side, click Histogram, drag the histogram, the left hand box, which is a simple histogram, into the Chart Builder box, and drag pain score into the x-axis and click OK. And you should come up with a histogram that looks like this. So the most important thing to realise about a p-value is that the p stands for probability. So let's think about that looking at this histogram. From the frequencies that we've done, we know that the median is 4.6, or the mean is 4.3. So what is the probability that any of these patients has a pain score that's greater than 4.6? Now we know that the median is the middle of the data, and that half of the patients have a pain score that's greater than the median, and half of the patients have a pain score that's less than the median. So we can say that the probability that any patient has a pain score greater than 4.6 is 0.5, half. Therefore, for this question, p equals 0.5. Similarly, if we think about the 75th percentile, which is 5.4, what's the probability that any patient has a pain score greater than 5.4? Well, we know that 75% of patients lie below that quantile. Therefore, 25% of patients in this series have a pain score greater than that number. Therefore, the probability is p equals 0.25. Now, to extend this, rather than thinking about the probability in terms of the number of patients, let's think about it in terms of the mean and the standard deviation of a normal distribution. So what do I mean by that? Well, say that I only knew that the mean was 4.3 and the standard deviation was 1.7, could I determine the proportion of patients in my sample or my population that had a mean pain score of less than 5.4? Well, I could, and the way you do that is by calculating a Zed score, and this is all in Chapter 6 of Statistics at Square 1. This is a very easy calculation to do. SPSS doesn't do it automatically, but you can do it just by hand. And you calculate it by taking the number you're interested in, which is 5.4, and subtracting the mean, which is 0.4336, and then dividing by the standard deviation. And you get 0.618. So what does that number tell you? Well, that number is the number of standard deviations that 5.4 is greater than the mean. So 5.4 is 0.62 standard deviations greater than 4.3. And we can convert that number into a probability using a normal distribution table. I've just Googled standard normal table and got this Google page up, and it's the first table you come to. First click on this graph to the side which explains how the table works. So this is an equivalent to our histogram. It's a line this time, and the Z value, which is what we've calculated, which is 0.6, we can convert it to this using this table to the probability of, in our case, a patient having a pain score of less than 5.4, and that's represented here by the shaded yellow part of the table, of the graph. So going back to the table has columns and rows, and it's just two decimal places, with the column being the first decimal place and the row being the second decimal place. So 0.62 is 0.6 here, and 2 there is 0.7324, which is a pretty good approximation to the 75% centile that we're aiming for. So this has shown us that our histogram or our normal distribution with a mean of 4.3 and the standard deviation of 1.7 is a very good approximation for the underlying data. Up until now, we've been treating our sample a bit like a population, and now we're going to move on and treat it like a sample again. So in a similar way to how we moved from talking about standard deviations to standard error of the means, we're going to do the same here. Let's think about this question. We have a sample with a mean of 4.34. What is the probability that the population mean is actually 5 versus it's something different to 5? So we have a sample, we know the mean of the sample, and we're asking what the probability of the population is of having a mean of a given value, and we're going to make it 5. Let's see if I can sketch that out. So we have a normally distributed population with a proposed mean of 5 and a sample with a mean of 4.3. So the way to do this is with a one sample t-test, and it can be done easily in SPSS by going to Analyze, Compare Means, one sample t-test, scooting across pain score, specifying the test value, which in this case is 5, and pushing OK. This is what you get, a descriptive statistics box with the number, the mean, the standard deviation and the standard error, which are all as we have seen previously, and then a one sample t-test results box. So what do these numbers actually mean? Well, in a similar way to how we calculated the Z scores before, we're interested in the difference between our sample mean and our proposed population mean in terms of the standard error of the mean. This is quite difficult to get across, but it's quite simple to see what's being talked about. So the difference between our sample mean, which is 4.336, and the proposed population mean, which is 5, is minus 0.664, and similarly to what we did before, by dividing by the standard deviation, we divide this time by the standard error of the mean, 0.2437. And so the difference between our sample mean and the proposed population mean is 2.72 standard errors of the mean. And you'll notice that the number we've calculated there is the t-value. And so we've done it by hand as it's been done by SPSS. So you calculate the t-value simply by taking your sample mean, minusing the proposed population mean, and dividing by the standard error of the mean. And that gives you the t-value. So how does that look in our graph? Well, we've taken 5 from 4.3, so if there was no difference between those, we would be at 0. So we've centred our distribution on 0. And we're simply asking, what's the probability of us being this distance away from 0? And this distance is the t-value, which is 2.75. And in this direction, minus 2.75. What does t equals 2.75 actually mean? Well, go to the student's t distribution in Wikipedia and go down to the table that we used before. We have 50 in our sample here, so the degrees of freedom is 49. Don't worry about that at the moment. So 50 here, look for 2.75, and it's between 2.678 and 2.937, and that means for a two-sided test it's between 99% and 99.5%. What does that mean? Going back to our graph, it means that between 99 and 99.5% of the data is in the middle of the graph here, meaning between 0.5 and 1% of the data is in these tails, and 1% is equivalent to 0.01, and 0.5% is equal to 0.0005. So we can say that these tails, and by tails I mean the ends of the graph here, the probability of being in these tails is between 0.005 or 0.5% and 0.01 or 1%. Meaning for this t-test, the p-value using a table is between 0.005 and 0.01. Check back in SPSS, and we've calculated the t-value, which is minus 2.725. We know the degrees of freedom is n minus 1, n is 50, so the degrees of freedom is 49, and our significance level is 0.009. So we had calculated it at between 0.005 and 0.01, so we've shown that as well. One last way to think about this is, if you remember last time, we said that the 95% confidence interval for the sample mean was around about 2 times the standard error of the mean. So the 95% confidence interval for 4.336, the upper bound of that is 4.336 plus 2 times the standard error of the mean. And I've just calculated it as 4.826. So if we were to ask what is the probability of the population mean being 4.826 if our sample mean is 4.336, Well, if you think about that, the bounds of the 95% confidence interval for our sample mean of 0.336 go up to 4.826. Therefore, the chance of the population having a mean of 4.826 or more extreme than that is what is left out of the 95% confidence interval, which is 5% or 0.05. And we can check that by going analyse, compare means, one sample t-test, 4.862, 826, okay, and sure enough, the significance value for whether 4.826 is the population mean on a sample of 4.336 is 0.05. I found that all quite difficult to explain, and I'm sure it could be done better. Please ask questions of stuff that wasn't clear. Please have a read at the book. Next time we will be comparing the means of two different groups. So we'll be looking at our laparoscopic versus our open hernia repairs and using a t-test to compare the difference between the means of those two groups.